Hi everyone. This will be a brief and concise review of problems related to pH, equilibrium, and acids and bases. So the theory and the derivation of the formulas comes from the PowerPoint presentations that are laid out step by step. So I won't be reviewing those, but at the top of the document what you can see is the formulas that are filled in. Right? So we've went through the meaning of all these, the way that they're connected, and now we'll apply them to a couple of different situations. What we want to consider when we're solving acid and base problems is a couple of steps. We can make ourselves an algorithm. We want to ask ourselves, is it a strong or a weak acid or base? Strong or weak, and then acid or base, because that's going to depend on what we're looking for, right? And then once that's the case, what we'll need is a reaction that identifies the ionization or the dissociation. And then from there, it will either be if it's a strong acid or base, we will use stoichiometry. If it's a weak acid or base, we will use equilibrium and ice tables. And then lastly, we can relate that back to pH or pOH. So that's the link between everything. Logical thinking. Just clean that up a little bit. Right, and those are the processes involved in acid and bases. So let's look at our first example here. Determining the pH and other properties of a solution of nitric acid. So nitric acid is one of the 6 strong acids. Right? And because we're being asked for pH, pH is essentially the concentration of hydrogen ions. So the first thing we need to do is know that a strong acid ionizes. Okay, so we have hydrogen and the nitrate ion. So the first hydrogen is displaced, it has a positive charge, and then the anion left behind has a negative charge. So because this is a strong acid, right, that means that we have written our reaction now. If we look next, we need to use stoichiometry. So we're given the concentration as 0.042 moles per liter. So everything's balanced as a 1-to-1 ratio, which means that the concentration of hydrogen is also 0.042. Right, so we can use mole ratios to determine that. So from there, this is what we'll actually use to determine the pH. Now, in some cases, it's not always the same as the molecule, so it's a common misconception that the concentration of the acid can be used to find the pH. But in reality, we want to make sure we're looking at the hydrogen concentration. So we'll start off just by calling this A. pH is equal to negative log of the hydrogen ion concentration. So the value is 0.042 like we have there. Okay, and don't forget to punch in the 0, and what we'll get is 1.38 as our answer for that. Now for pOH, you got the formula at the top. The two add together to 14, so we can say pOH equals 14 minus the pH, just rearranging that. So we found the pH above there. We'll subtract that from 14, and we'll get a pOH of 12.62. Lastly, we're asked for the hydroxide ion concentration. There is more than one way to find this. We'll try to use the values that we were given, which was the concentration of hydrogen. So we can say that Kw equals the hydronium ion times the hydroxide ion concentration. We'll isolate for OH minus here, right? Kw, which is a constant, 10 to the negative 14, divided by the hydrogen ion concentration. And when we punch that in, and always punch these in to try for yourselves, 2.38 times 10 to the negative 13 moles per liter. So those are our answers to this question. 1.38 is the pH, 12.62, and 2.3 times 10 to the negative 13. Now you might be thinking there's no hydroxide in that formula. Where did it come from? So remember that this is from the autoionization of water. Okay, because all acids are in a solution of water, we can see that water enters in equilibrium with itself. Okay, one water gives a hydrogen to the other, and that leaves behind hydroxide and hydronium. Now they are very, very small or very low concentrations of these. They're negligible, they have no effect on the pH, but that's where the hydroxide concentration is coming from. So there are hydroxide ions present, but in no great quantity. All right, so for example 2, again, we're going to use the algorithm up here. So pause and jot that down if you think it'll help you throughout. What is the ionization constant of K? So let's think through this logically. We're being asked to find the Ka, which is the products, concentration of the products over the concentration of the reactants. Right? So to do that, we need to write a reaction. We need to know what our products and our reactants are, right? Because it's a weak acid, we'll be using equilibrium, right? And so we'll make a note of that here. It'll be a two-way arrow. So to find concentrations from an equilibrium, we need to use an ice table. Okay, so that's our roadmap and how everything connects. So HA is a general acid. Let's write this down here. It's aqueous. We show water in the ionization of weak acids. And it leaves behind hydronium and the anion, whatever it is. So we've got that there. We'll set up our ice table now. We've got a 0.2 molar solution. Now we're leaving out a lot of the numbers here for conciseness, but we'll keep in mind significant digits at the end. Water is a pure substance, so it won't factor into our calculations. And we have 0 of the initial products. There's no common ion here. So we lose reactants and we gain products. Everything's a 1-to-1 ratio, which is nice. We have X and we have X. And again, we get the E column by adding I and C. So 0.2 plus negative 1x equals negative X. Now, normally we would have enough information to solve this. So we go to our question, right? We can't use Ka to solve for X because we're being asked to find Ka. So in this case, we're going to use the percent ionization. And what that means is that the percent ionization as a review is equal to the concentration of the hydrogen ion over the original concentration of the acid. So all that's telling us is that 5% of that 0.2 moles per liter will turn into the ion. So we can say 0.05, convert that to a decimal, over X over 0.2 moles per liter, which is the concentration of the original acid. And when we isolate for X, we can do 0.05 times 0.2. So we've got 0.1 moles per liter. So that means as this acid establishes its equilibrium, only 5% of it turns into the acid. That's what X equals in this case. So we can go back in, knowing all of our values now. We can say that that is equal to 0.01. So is that there? And these are all for concentration. And then when we do 0.2 minus 0.01, we're going to get 0.19. So now we know our concentrations. We can say Ka is equal to, well, we'll shorten it here. Remember that H3O plus and H plus are the same thing. Representatively, they're technically different things. So we'll have 0.01. We're just subbing in the E column now from here over 0.2. So we've got 0.01 squared, essentially, divided by 0.2. So we have a K value of 5. We check our significant digits. The 5% was 1, so we'll leave it at that. 5 times 10 to the negative 4. And that's our final answer. All right, so feel free to rewatch that one. Example 3. We're going to go through the same process again. And we always like to ask ourselves, what are we being asked right off the bat? So if we read through the question, formic acid is released by some ants. If the Ka is given, what is the pH? So to find pH, we know that it's the hydrogen ion concentration, right? We're looking at a weak acid due to the K value, right, being significantly less than 1. So we're going to have to write a reaction, set up an ice table. So it's an equilibrium because it's a weak acid. Set it up an ice table and find out the equilibrium concentration of hydrogen, right? So there's our little roadmap. And as we spoke about in class, we solve it from the bottom up. So formic acid. And again, if you're struggling with how the acid equation comes, we always write the acid plus water because that's the little reaction that happens here. They form an equilibrium. The acid gives away its hydrogen to water. So if it's a weak acid, it forms H3O plus. If it's a base, it'll accept a hydrogen from water, right? So there has to be water there. And then the rest of the formula is left over as an anion. So we set up our ice table. Again, we're just going to cross out water as a pure substance. We have no products initially, and we have an initial concentration from the question. Minus 1x plus x plus x. Right, and we can see as we fill in our equilibrium row, which is first plus the second rows, we have an x value. So we'll use that. I'm just going to kind of section our analysis off over here. Right, we can say that Ka is equal to, right, and jumped ahead a step, but when we don't know the row, the x value, we use the K value. Doesn't really matter, but we use K to figure out what x is. Right. So K is products over reactants. We've got H plus over CHO2 minus divided by HCO2. So when we substitute everything and we were given a K value here, -4, I'm going to simplify that to x squared over 0.025, take away x. So we have that take away x term. We want to check the 100 rule in this case. I'm just going to give us a bit more room. There we go. So now we can work with this without having to cram it in. All right, so we want to check the 100 rule at this point. That way we can eliminate this change in x, which would simplify the equation considerably. So we'll just call it check 100 rule. So for this, we'll say the smallest concentration divided by the K value. And we're checking if that's greater than 500. So 0.025 divided by 1.8 times 10 to the -4. So unfortunately, we've only got 139. So we can't ignore x in this case. So what we're going to have to do is cross multiply, expand out the terms, and solve for a quadratic function. So we'll multiply this out. We've got 1.8 times 10 to the -4 times 0.025. We've got 4.5 times 10 to the -6. Take away that times 1x, which just gives us that there, equals x squared. We'll rearrange this into standard form, where we have a plus b plus c so we'll have that there, and we're going to solve for our roots either by factoring or using the quadratic equation. So in this case, I'm going to use the quadratic equation on the calculator just to speed things up. So our a value is 1, because there's no value in front of that there. Our b value is -1.8 times 10 to the -4. I have to remember to take the sign with it. And our c value is positive 4.5 times 10 to the -6. So in this case, root 1 equals root 2 at 9 times 10 to the -5. So those are the same value when solving it. Okay, so that tells us that that is the change. That's what x represents. And we know that that now is the number that we can sub into our ice table. So because we're being asked to find pH, we could solve for all of the concentrations of the products, but they're irrelevant here. We're only concerned with the concentration of hydrogen ions. So we'll look at hydronium because they're the same. Refer back to the top of the page for that. Equals x equals 9 times 10 to the -5. And now we can solve for pH because we know the equilibrium concentration. Okay, so we need to take the negative log of 9 times 10 to the -5. We get, don't forget your negatives, and you have to be comfortable with your calculator, 4.05 for our pH. And that's our final answer. Okay, so working with a weak acid, the pH should be below 7, and it is, but it's not as low as it would be if it was a strong acid because the hydrogen ion concentration is lower. Weak acids only partially ionize. If it was a strong acid, we'd be taking the pH not of 9 times 10 to the negative 5, but of 0.025 because it would be 100% ionization. So for example 4, we're going to look at bases now. So those 3 examples were related to acids, and we'll go to bases at this point. So we've got barium hydroxide, and we know barium hydroxide's formula, if we do our crisscross, is BaOH2. So we're being asked to find pH and pOH and all the different variables of it. So we'll start with a reaction. Right, because it's a strong base, it has hydroxide in it. It'll ionize into its ions, which is a metal and hydroxide. Okay, so we're given the initial concentration. Now, for our hydroxide, to figure out the concentration of that, we're only ever interested in hydroxide or hydrogen for pH changes. Metals won't affect it at this point. So you can see that it's a 2-to-1 ratio. So what that means is for every 2 moles of hydroxide, there is 1 mole of barium hydroxide. And that's from our balanced chemical equation. So if we set up our mole ratio, right, the first fraction comes from our coefficients. The second one, we're trying to find out what the concentration is over 0.16. So we'll isolate for X. We can see that it's double, so it'll be 0.32. And that's the ease and the stoichiometry, okay, because we're working with a strong base, right? All of the substance turns into hydroxide ions when they dissociate. So for A, the concentration of hydroxide based on stoichiometry is 0.32. To find the pOH, we're just going to sub that into our formula. Right? That value is there. So negative log of 0.32 gives us 0.49. And we'll report to 2 decimal places. Now, for pOH, remember that this is a measure of basicity or alkalinity. So that's a very basic value, whereas 14 would be acidic on this scale because it's inverted. So pH is 14 minus the pOH. And again, all of these formulas are at the top of the page. So we've got 13.51, which is very basic and consistent, so that's good. And then lastly, we have a few different ways to calculate the hydrogen ion concentration. So we'll just do this one for ease. 10 to the negative pH, so 10 to the negative 13.51. Now remember, this is an exponent, not a scientific notation. So we're not using our exponent button, our EE button. We're using the actual exponent button in this case. So not times 10 to the power of something. So we get a value of 3.1 times 10 to the negative 14. And again, even though it's a base, water ionizes itself. So there is a little bit of hydrogen present. And there are our 4 answers. So very straightforward for a strong species. For a weak base, we can see that it's given to us right in the question. So we'll be writing an equilibrium reaction. And we're being asked to calculate the Kb value. So let's just outline that. We need to know the products over the reactants to find that. To find out those concentrations, being weak, right, we'll need a reaction, and it's an equilibrium. And to do that, we'll need to use an ice table to find the actual concentrations. So we'll start with the base, C5H5N plus H2O. And that won't be in our expression, but we show it here. So again, the base accepts the hydrogen from the water. So we'll just put it on the end here as a positive, and it leaves behind hydroxide ions. Okay, so we'll set up our ice table. Our initial concentrations, 0.125. We're just going to squiggle that out. There's no common ion here, so we don't know any of that. Minus x plus x. It's all 1 to 1 in this case because the hydrogen just traded places. 0.125. Take away x, x, and x. So again, we're finding Kb, which means we can't use it to solve for this x value, so we need some other information. With the acid equation above, we were given the percent ionization. In this case, we're given the pH. And what we know is that we can relate pH to the hydroxide concentration through pOH. So we can say pOH equals 14 minus pH. So our pOH in this case will be 14 minus 9.1. That gives us a value of 4.9. Now we're going to use that for the hydroxide concentration because we know 10 to the negative pOH will give us that value. So 10 to the exponent negative 4.9, not 4.91. Let's just clean that up. Gives us 1.26 times 10 to the negative 5 moles per liter. So now that we know that, that's also equal to x in this case. So we can sub that into the ICE table, right? And we see here that there's x a few times. And then in this case, when we do 0.125, take away that value, we get 0.12499, which we're going to keep as 1.25. Right. So essentially the concentration remains unchanged because of it's going to be a very small K value. So now we know our equilibrium concentrations. We can solve for Kb. We'll do OH minus times the conjugate acid over the original base. So we'll sub in our numbers, 1.26 times 10 to the negative 5. That's twice, so we'll just square it mathematically, divided by 0.125. So we take that value, divided by 0.125, and we get for a Kb value, 1.01 times 10 to the negative 4. Right, so again, the process is very repetitive, understanding the link between hydroxide and pH in this case. Okay, finally, we'll come to this point here, where I'm just going to give us a bit more room by bringing this up. Awesome. And we'll get rid of that there. So, for our last question in this video, we're asked to calculate pH, and we're given a solution of hydrazine. So hydrazine is a weak base. We can write equilibrium for it. Now, hopefully you're pausing at this point and trying the problem yourself. It's one of the best ways to consolidate, right? And reviewing those algorithms we talked about. So I won't review the algorithms here or the reasoning. We'll just focus on the answer. So we will want an ICE table. In the end, to find pH, we need to calculate the hydrogen concentration. But because it's a base, we have hydroxide. That will give us pOH. And we can relate that back to pH through that value of 14. So we've got an initial concentration, no products. We lose our reactants. Okay, and everything's 1 to 1, so we've got 0.1 minus x, x, and x. So now we do know Kb. We'll solve for x that way, and that'll let us find out the hydroxide concentration and then relate that back to the pH. So we've got x squared over 0.1 minus x, 1.7 times 10 to the negative 6 equals x squared. Okay, so I'm going to check the 100 rule here because I see I have this change term. If I do 0.1 divided by 1.7 e negative 6, we've got 59,000. So the 100 rule checks out. which means I can ignore that x value. You get 1.7, I'll just rewrite that here, over 0.1. And remember, the 100 rule just tells us that within 5% error, that x will not significantly affect the initial concentration. So it simplifies our calculation. So as we cross multiply and isolate for x, we'll get this value here, and then we'll take the square root of it, and we'll see that x equals 4.12 times 10 to the negative 4. So what we want to do with that is sub it back in, because it'll tell us what the hydroxide concentration is, which allows us to determine pH. So we can say, therefore, POH equals negative log. Okay, we know what the hydrogen or the hydroxide concentration is now. It gives us a value of 3.38. And then pH is 14 minus that value. So we get 10.62. So that's how we can calculate the pH of a basic solution, knowing its Kb, it's a dissociation constant, and its initial concentration. So that rounds out pretty much all the scenarios we'll look at. Hopefully that helped as a review, and good luck with your studies.